Okay, good evening, everyone, and welcome to the first highlight lecture at the 73rd International Astronautical Congress. My name is Jason Callery. I am the Mission Area Executive for Civil Space at the Johns Hopkins Applied Physics Lab. There are a lot of topics in space exploration that get me very excited and energized, but extreme exploration of our sun takes the cake. This is one of the most challenging and one of the most rewarding scientific frontiers that we have on our horizon. And it's very timely that this highlight lecture is being presented to you today, both because of the timing and because of the location. So as you all know, the first International Astronautical Congress happened right here in Paris, France, and it happened in 1950. And that was at a time when solar physicists, early generation of solar physicists, were postulating whether or not there was a wind that was emerging from the sun, permeating through our solar system and impacting our planets. And here we are, 73 years later, on the cusp of bold discovery with two marvels of engineering that bring the entire international community together. And so we have a very special treat for you that you're gonna enjoy. And it's going to be a presentation that's led by two of our leading solar physicists in the community. But before we go there, I'd like to start with this image. It's an image that will resonate with many of you, with all of you, hopefully. It's an image of what the night sky looks like when you look up from your backyard and you see this peppering of these lights, right? These tiny little specks of light. And when you look at an image like this, it can be easy to lose sight that every one of these specks of light is a giant burning ball of hydrogen, okay? It's a system that's generating energy at an equivalent rate of having billions of hydrogen bombs going off every second for billions of years. Some of these stars that you see are a little smaller than our sun. Some of them are a little larger than our sun. Some of them live shorter. Some of them live a little bit longer. But they are the heartbeat of their own ecosystems. And we know today, just like our sun is not isolated in space, there's a network of planets that orbits our sun. Scientific discovery has told us that planets are the natural outcome of the star formation process. So wherever you have a star, you have a planet. And what you're seeing here is just those stars that are in our neighborhood, right in our backyard, in our solar neighborhood. In our galaxy, we know that there's hundreds of billions of stars, and those stars are all surrounded by planets, and therefore there are hundreds of billions of planets. And so here on Earth, right, the sun is the lifeblood of our solar system. It's the heartbeat of our solar system, right? The sun is responsible for the air that we breathe, the atmospheric circulation on our planet. It's responsible for the seasons. It's responsible for the oceans, right? And it's responsible for the energy that leads to us being here today and life thriving on our world. Guess what? The same is true in every one of these systems, right? The sun is the heartbeat of all of those star-planet systems. So what do we know about them? How can we study them? Well, that's difficult, right? It's unfathomable to think of a measurement technique, an instrument, or a mission that we could fly to one of these stars and understand the true natures and the detailed physics of that star. But we can do that with our sun, okay? And so that brings us to today. Today we're going to talk about extreme exploration of our sun with two marvels of engineering, two new innovations, recently launched missions, NASA's Parker Solar Probe and the European Space Agency / NASA Solar Orbiter mission. And this exploration, this discovery is going to be brought to you by two of the leading solar physicists in our community. So I'm going to now get off the stage, and I'm going to turn it over to the experts. Let me introduce them quickly. The first speaker is going to be Dr. Noor Raoufi. Noor is a senior scientist at the Johns Hopkins Applied Physics Lab. He is also the project scientist for the Parker Solar Probe mission that he'll tell you all about today. Noor obtained his PhD right here in France at the University of Paris, and he enjoys tackling very tough challenges in solar physics, including studying the dynamic solar corona. Our second speaker today is going to be Dr. Daniel Mueller. Dr. Mueller is a staff scientist at the European Space Agency ESTEC Center. This is the European Space Research and Technology Center. Dr. Mueller is the project scientist for the Solar Orbiter mission. Dr. Mueller obtained his PhD in Germany, and he also enjoys tackling tough challenges in solar physics, but one of the things that he's truly passionate about is working on and developing high-performance scientific data visualizations. So you guys are in a treat today. You guys are in for a treat today. Noor and Daniel are going to take it over, and then I'll be back to close things out once they're done. So with that, I'll turn it over to Noor.
Thank you, Jason, for that nice introduction, and good evening, ladies and gentlemen. It is a pleasure for us to be here and share with you some of the latest discoveries by two of the most exciting NASA and ESA missions, Parker Solar Probe and Solar Orbiter. But before going into that, let me put it all into a historical context. When you look back at the history of solar and heliophysics research, there are moments where certain discoveries were made and they changed everything. They basically opened the new gates for exploration. The first that come to mind is the discovery of sunspots by Galileo in the early 1600s. And from there on, we discovered the solar cycle, the 11-year solar cycle. And to this day, we are still struggling understanding what is the driver of the solar cycle and solar orbital. Daniel will talk about it a little bit later. Fast forward to 1859, when Richard Carrington discovered the most powerful flares on the sun, that is white flares, and that resulted also in the most powerful geomagnetic storm ever recorded in history. And that actually was the start, the kickstart for what we call now space weather. Space weather is caused by activity on the sun, that is flares and CMEs, that can affect us here, the Earth environment and beyond. But we had to wait for decades to get to understand what is the main driver of all of this, of the sunspots, solar cycle, flares, and activity. It is actually solar magnetism. That was discovered in 1908 by George Hale using the Zeeman effect that you can see there. And magnetism is at the origin of all phenomena that are driven on the solar atmosphere there. Now, again, about half a century later, and at the dawn of the space age, as Jason mentioned earlier, we discovered what we call the solar wind. The solar wind is a flow of particles that are electrons, protons, and heavy ions that are continuously flowing away from the sun to fill the whole heliosphere. And again, 60 years later, we are still struggling to understand what is the main driver of the solar wind. A little bit later, I will tell you we are so close to understand what are the physical mechanisms that are at the origins of the solar wind and other phenomena. And all of this thanks to two missions that are Parker Solar Probe and Solar Orbiter. And the four examples I gave earlier were all golden ages of space exploration, and in particular for solar and heliophysics research. Guess what? We are living another golden age thanks to extreme exploration by flying closest to the sun using Parker Solar Probe, and by also flying out of the ecliptic and have the first view of the solar poles. Daniel will tell you why the poles are so important. That will allow us to explain the solar cycle. And also, we should not forget DKIST. DKIST is the 4-meter telescope built in Hawaii, and it's operational now. It will give us images with a resolution of 10 kilometers. Just a few years ago, not long ago, we could only see that in numerical simulations. Now, with these type of observations, we can compare numerical observation and numerical simulation and observations side by side. Now, what are the big questions that we want to answer by sending Parker Solar Probe so close to the sun and Solar Orbiter out of the ecliptic? There are five of them, but before going through them, let me say this. Both Parker Solar Probe and Solar Orbiter are by nature exploration missions. We are venturing into regions of space that we never flew through before, and whatever observation we are making there is a potential discovery. And that is exactly what we are learning from the data. These two missions are basically writing the textbooks before our eyes. So the first question that we want really to understand is a phenomenon that was discovered eight decades ago. That has to do with what we call the coronal heating problem. When you look at the solar corona, it's over 300 times hotter than the solar surface. And that is counterintuitive. We don't understand exactly why that is happening. The second one, which is closely related to the coronal heating, which is the acceleration of the solar wind. And again, that flow of particles that I described earlier, low down at the base of the corona, these particles are almost standing still. They are moving at few kilometers per second, but over a very short distance. They start flying at hundreds of kilometers per second. Where do they get that energy? We don't really know. The third one, and I talked about the discovery of Richard Carrington. Whenever you have a big explosion on the sun in the form of a flare or a CME, it accelerates a certain population of light to a good fraction of the speed of light. We call these particles the energetic particles, and they are extremely hazardous to human in space, to space equipment, and sometimes even to us here on the ground. Another global phenomena that is the solar cycle, and when you look at you count sunspots, they have a cycle of 11 years long on average. What drives that solar cycle? That basically was discovered by Galileo. It's still unclear. And the other thing that we all are aware of now, I think all of you were aware of what happened to the SpaceX 40+ satellites that were lost due to solar activity. And that is basically what we call the space weather, and we have to get handle of that. Now, to answer these questions, we cannot use the old method of observing the sun and its environment basically from afar and try to understand it. We have to get close and in person with the sun by missions like Parker Solar Probe and Solar Orbiter. And obviously, when you do missions like this, you cannot just do them easily like we're used to. New technology has to be invented, and new challenges has to be taken. For example, for Parker Solar Probe that you can see on this slide here, without that hexagonal shape on the front of the spacecraft that is the TPS, we could not have Parker Solar Probe. And also without the solar panels that are water-cooled, we could not have Parker Solar Probe. And there is another aspect of Parker Solar Probe that is autonomy. When we are close to the sun, we cannot talk to the spacecraft. It has to be 100% autonomous. If it encounters a problem, it has to solve it by itself. Let me get a little bit into the TPS. That is the key piece of technology that really led us to get Parker Solar Probe launched and operational around the sun. The TPS is basically a piece of carbon foam that is 11.5 centimeters thick. That's all it is. And it's very brittle. It is, it's fragile in a way. But in terms of heat, it's so effective. When we are at closest approach to the sun in 2024, by the way, that is the eve of Christmas of 2024, the side that is facing the sun will be at about 1400 degrees Celsius. 11.5 centimeters behind, we will be at just 300 degrees Celsius. And 1 meter behind, we will be at room temperature. And it's there where most of our instruments are operating. They basically operate in the shade of the TPS, and they are at room temperature. How we do the mission? Historically, what people thought of Parker Solar Probe is that, of Solar Probe, sorry, not Parker Solar Probe. They will send it all the way out to Jupiter, and using gravity assist, they will launch it out of the ecliptic. But there is one thing there. The mission will have a deep flyby in the solar atmosphere, but it will be one flyby And if you are lucky, it will be 2 flybys separated by 5 to 6 years. And these flybys, we have hours of measurements. That's all we have. In 2007, at APL, we came up with another strategy of implementing the mission using Venus. Using Venus 7 times, we can fly the mission for 7 years. And 7 years is way, way much better for science than just the single flyby. Let me go a little bit into the science now that I want us to talk about. So the main thing that we want to answer is the heating and the acceleration of particles in the solar atmosphere. And the first one of them that comes to mind is the heating of the corona and the acceleration of the solar wind. The solar wind, you see it in this movie here. It's all these motions of plasma that is flowing away from the sun. So as soon as from the first encounter of Parker Solar Probe around the sun, we saw something very special. It's what we call the magnetic field switchbacks. And the magnetic field switchbacks, it's exactly like a mountain switchback. It's an S shape in the magnetic field. And by the way, these were observed by Ulysses and by Helios, but they were so rare far away from the sun. But what Parker Solar Probe showed us, when we get very close to the sun, you have gazillion of them. They are everywhere. And what is nice about them is that they carry a lot of energy with them. You see on the top panel there, the red is the strength of the magnetic field, which is almost constant. The black is the radial component of the magnetic field that is basically rotating 180 degrees all the way back to the sun and out again. But guess what? Look at the panel, the bottom panel there. In tens of seconds to a few minutes, the switchback will transform a slow solar wind to a fast solar wind, going from about 300 kilometers per second to about 700 kilometers per second. That is a lot of energy to do that. So the big question about them is, where do they come from? How do they form? What is their impact on the solar wind? What do they do there? And guess what? The nice thing about this type of observation is that we started looking back at the sun, what is happening there, to get this type of phenomena like the switchbacks going on. And this, what I'm going to talk about now, are results that are not published yet. They are really fresh out of the oven. What we discovered are tiny explosions, magnetic field explosions. We call them, basically they are picoflares. They are very tiny, but the nice thing about them, they are everywhere. They are everywhere in terms of space on the solar surface, but also in terms of timing, exactly like the solar wind. We believe that these magnetic field explosions are what is driving the solar wind, but not only the solar wind. It's also the main driver of the coronal heating problem. So the nice thing that Parker Solar Probe and Solar Orbiter are doing is basically bringing the communities that are the solar wind communities and the solar people together to talk to each other. And that has never been done before. Let me move a little bit forward. One of the things that we always dreamed of is to fly a spacecraft through the solar corona that we see during a total solar eclipse. And starting from April of last year, Parker Solar Probe, every encounter has been flying through the solar corona. The way we know it, and look at it now, on the top part of the movie, structures are moving up, on the bottom part, they are moving down. So if you are driving through the highway and you have signs in front of you, when they are far away from you, they are basically at the same height. But when you get closer to them, they start going up and up, up and up, and at a certain point, they fly above you. That is exactly what is happening, and that is when Parker Solar Probe is flying through the solar corona that we see during a total solar eclipse. But that also comes with some bounties there. You see all the CMEs, the amount of details we see in this coronal mass ejections is unprecedented. And look at the bottom there. What we are seeing there is the collisions of 3 CMEs, one after the other. This type of details, we never seen it before from one AU. Now, you might have wondered, there were streaks in the previous movies. What were these? So in a way, they don't make the images very clean. So the spacecraft is always bombarded by dust in the heliosphere. And whenever we have a dust hit on the spacecraft, it creates a cloud of particles that the imagers can see. And using the spacecraft as a detector of these particles, we actually discovered a new population of dust in the heliosphere. And this population, we call the beta stream, is the result of the interaction of the Geminid dust trail that you see in green there with the zodiacal cloud. Guess what? This trail here that you see in green there can actually impact the surface of the moon. It causes some weathering of the surface of the moon, which is pretty impressive. This thing, we never ever seen it before. It's the first time we see this type of interaction between two dust streams. Last big thing about, and here I have to tell you the story. Whenever we fly by Venus, we turn all our instruments on and basically turn Parker Solar Probe from a solar and solar wind mission into a planetary mission for a brief moment. And we had one program that we wanted to detect the clouds in the atmosphere of Venus. And this image on the left-hand side, when we got it, we were so excited. We thought, yeah, we got the clouds in the atmosphere of Venus, only to be disappointed just a few moments after, because the Japanese mission on the right-hand side exactly observed the same structure a few years ago. What it is, it's a highland, actually it's the Aphrodite Terra, which is a highland in the surface of Venus. For us, it was bittersweet, but it's fine. But when our Venus colleagues saw these images, they were so excited about it. We gave them the data, they worked on it, and guess what? They made a big discovery out of it. They discovered the shortest wavelength thermal emission from the surface of Venus. In other words, Parker Solar Probe is opening another window to study the surface of Venus. This is really, it's amazing, it's fascinating. Well, with Parker Solar Probe, we can look at a lot of details very close to the sun, but that's not all we are interested in. There are other phenomena that are global, and they can affect us here on Earth, as I said at the beginning, like flares, like CMEs, and that's actually where a mission, the sister mission that is Solar Orbiter, come in. And there are so much exciting data from Solar Orbiter as well, and Daniel Moorer is going to tell us all about it. Daniel.
Thank you, Noor. It's a wonderful introduction to the second part of this presentation that I'm happy to share with you. The second spacecraft I'd like to introduce to you tonight is the Solar Orbiter mission. As Noor said, it's a mission of international collaboration between the European Space Agency and NASA. European spacecraft with Airbus UK as the prime contractor, US launch vehicle procured by NASA, an Atlas V that got us beautifully into orbit just before the start of the COVID-19 pandemic. We have 10 instruments on board, 9 are European-led, 1 is US-led, but 4 have transatlantic hardware cooperations. So it's really a whole village that it takes to build such a mission, and then we can collaborate with friends like Parker Solar Probe mission. We have members of the flight control team in the room today. We have principal investigators in the room today, agency colleagues. So it's really great to see all this come together after a little time in space. So the Solar Orbiter spacecraft is also design-driven by the need to get rid of the heat. Since we are in Paris, allow me to do a food analogy. The Parker Solar Probe heat shield is a foam layer, a bit like a chocolate souffle. On Solar Orbiter, it's more of a croissant or pain au chocolat structure. We have thin layers of titanium foil wrapped around a carbon fiber aluminum honeycomb sandwich, and we can tilt the solar rays to manage the heat. And overall, a lot of engineering challenges had to overcome so that ultimately scientists like myself can work with the data. So I'm extremely grateful to all of the engineers involved in making that happen. So the first thing is we needed to get a heat shield that is both light and resistant and not shed any particles, because we have a lot of cameras that look at the sun and they would get a lot of stray light or UV blinded by particles or molecules at the spacecraft. So we needed to have something that is inert and not shedding any materials as the mission progresses over 10 years. Now, we tested that at our Large Sun Space Simulator at ESTEC in 2014. Still took a couple of years to get everything together. The heat is temperature of molten metal on the front side, not quite as hot as Parker Solar Probe, but still more than 500 degrees centigrade. And as Noor said, roughly room temperature behind just, in our case, 40 centimeters of heat shield. The other challenge for Solar Orbiter was we want to measure extremely small magnetic fields, nanotesla fields. We could detect an MRI scanner at the other end of Paris with these sensors. So that means also that anything on board needs to be really quiet in terms of EMC signatures. So in order to do that, we had to encapsulate the reaction wheels into a mu metal cage. We also had to make sure that the spacecraft doesn't charge up in the solar wind, because we want to measure low energy particles as they fly past the spacecraft, and we don't want them to fly around the spacecraft because it's all a charged bubble. So to do that, we wrapped, for example, the backside of the solar arrays in a conducting foil, and the entire spacecraft is supposed to disappear as seen from the instruments. Okay. Our trajectory is like Parker Solar Probes, driven by planetary flybys at Venus. We had one just 2 weeks ago. And over time, Venus is being used to essentially slow us down, let us fall a bit more rapidly towards the sun. We're now in the nominal mission phase where our perihelia are inside Mercury's orbit. So we go down to roughly a quarter of the Sun-Earth distance, meaning we get up to 13 times the solar flux that you get at 1 AU. And as the mission progresses, we'll gradually increase our inclination out of the ecliptic plane. And that will give us the first ever views of the sun's polar regions. So now, why is that important? We believe it's key to understand the sun's activity cycle. So what is this solar cycle in the first place? The sun and many other stars generate magnetic field due to moving charges in the interior. And the sun is a ball of plasma that doesn't rotate like a rigid body, but in fact, the equator regions rotate faster than the poles. And what you get as a result is a sort of dipolar seed field that then gets wrapped up and tangled, and you get regions of strong magnetic field that collect at the bottom of the bubbly envelope that we call the sun's convection zone. And these spaghetti out of magnetic field have a lower density than the surrounding material, so they rise up to the surface, and when they penetrate the surface, they form what we know are sunspots. So these sunspots are dark, and they're dark because they're cooler than the surroundings. And the reason for that is that the magnetic field is challenging the particles, channeling the particles along the field and doesn't allow them to move perpendicular to the field, a bit like a highway is channeling cars in one direction. Now, when that happens, magnetic fields can also reconnect and lead to flares and coronal mass ejections. And overall, this cycle of waxing and waning magnetic activity has a period of 11 years. What we still do not know after decades of studying the sun's activity from space and after 400 years of tracking the sun's activity from the ground, we don't know why is it 11 years. There are some stars that have shorter periods, some have longer periods, and most importantly, the amplitude of the cycle really determines space weather, whether we need to take any measures to protect satellites. We simply don't know whether the next cycle will be more intense or less intense than the previous one. And if you look at the plot, you see in gray the sunspot index as a background, and in blue the open magnetic flux in the heliosphere, the plasma bubble that the sun blows into the interstellar medium. That's a rough correlation of 11 years and the same periodicity, but they are not the same. So we do not fully understand yet the linkage between the sun's activity and the heliosphere. And that is what the Solar Orbiter mission is about. We are trying to connect our star to the bubble it blows into the interstellar medium, which encompasses all planets of the solar system, including our own. Now, this is a cartoon that we drew for our assessment study report in 2009. So it was supposed to be relatively straightforward. We said we would observe a flare on the sun's surface in UV, in X-rays. The magnetic field reconfigures, it ejects particles into space, and these energetic electrons emit radio emission. We would detect that with our radio instrument on board. Shortly thereafter, the electrons arrive. They travel almost with the speed of light. We detect those, and we can use those as a timer for the heavier ions that arrive a bit later. And that timing can give us information about the conditions in interplanetary space between the sun and the spacecraft. And this plot really makes me genuinely happy, because we got extremely lucky that already 2 months into our nominal mission phase in March of this year, we got exactly this cartoon as real data. So we had a solar energetic particle event on the 21st of March. We imaged by chance in high resolution that area of the sun in UV and X-rays. And even as a bonus, we got a visual representation of the ejection of the material in space. So that's not a cartoon, that's actually real data. We saw Langmuir waves in the plasma where the spacecraft was flying through, and the composition of particles all the way from hydrogen to iron measured by the energetic particle detector suite. And the nice thing is we really try to make all the data available to everyone worldwide. And the PI of the EUI instrument is also in the room here. And this is data from the full sun imager. We did not expect we could take that throughout the orbit, but luckily we got the upgrade to our ground system of the S-Track ground stations. And so we get these images 24/7 throughout the orbit, and you can see the eruption one by one taking off. And we developed a tool where everyone can just go look at the images and make sequences like that within a few minutes. Now, let me take you into our first close perihelion in March. So that was the first time we got closer than half the distance between Sun and Earth. We went down to 0.32 AU, so a third of the Sun's distance. The full sun imager is done such that it encompasses the entire sun even as we get close in. And then on top of that, we have a high-resolution imager that has a pixel size of half an arc second, which at perihelion corresponds to about 100 kilometers. So that is as high resolution as we could get from a few rocket flights in the past, but we get this repeatedly every couple of months. So what you see here is really a plasma physics laboratory in action. You see plasma of roughly 1 million Kelvin. This is emission from 8 to 9 times ionized iron atoms. You see the magnetic field is shaping all the dynamics. There are overlying magnetic loops that are sometimes filled with plasma and they radiate. There are dark structures that are actually filled with even more plasma, but it's cool, and so it absorbs the light coming from underneath. And the combination is just really stunning and beautiful, and we have sequences with cadence of roughly 5 seconds, so we can really follow the plasma dynamics in near real time. Now, ultimately, we'll see the poles from higher angles that will allow us to measure also the magnetic field, because when you look out of the ecliptic plane, you see essentially the magnetic field more or less edge on, making it really hard to measure the direction and strength with high precision. But already now, we can see in these movies, let me go back once. You can see the interplay between the open magnetic field that is dark because the material just escapes into the solar wind, and the small closed fields that then result in jets that just move into the solar wind and do interesting phenomena while traveling outward. So among the first things we saw in these high-resolution images were tiny flares. They could be picoflares like those that Noor alluded to. They have been dubbed campfires. I don't know whether that's a good or bad word, but it means that they're essentially everywhere. Everywhere we look, not only in magnetically active regions, but also in so-called quiet sun regions. There are these tiny events that are roughly tens to hundreds of seconds in duration. They are hot in temperature. They reach 1 million degrees, even though they just reach a few thousand kilometers above what we call the surface of the sun, which is just a couple of thousand degrees hot. So that's really interesting, and we have models that indicate that this is also related to magnetic reconnection. So we have field lines recombining and releasing energy into radiation and kinetic energy. And this is just the beginning of the story. The next thing to do is we need to collect more data over the next couple of perihelia and then do statistics and find out, are these events so frequent that even though they are small, they could potentially explain the 1 million degree hot temperature of the corona, even in the areas where there is no strong, large-scale magnetism like with a sunspot. Now, coming back to these switchbacks that Noor talked about earlier, Parker Solar Probe has revived the interest in these. They have been seen in the past, in the 70s with the Helios spacecraft, and then in the 90s with Ulysses. And the open question is still, how do they form? Are these structures that are thrown into the solar wind with a sort of slingshot-like mechanism from the surface, or do they form by means of turbulence as you move with the solar wind? And we released data just a week ago. There's a paper working on data from the coronagraph of the Solar Orbiter mission, where the light of the sun is blocked out to reveal the faint emission moving outward. And they saw a feature that is uniquely similar to what has been seen in Parker Solar Probe data. Just the Parker Solar Probe data is sampling it in situ, essentially feeling the solar wind, while this is a remote image of a structure that is moving with just the right speed, and it looks like also the right density compared to those features that Parker Solar Probe has observed while flying through them. And there's space for more theory and modeling, and maybe there are different types of these, but at least this observation is consistent with a model of an interplay between open and closed magnetic field, getting close and reconnecting again. And then these kinks are moving outward a bit like cracking a whip. And so this bend is just traveling outward and producing an S-shaped feature. And that's what we see, at least in this instance. And it's just one example of a cooperation between these two missions, that we can do something together that each of us couldn't do alone. Now, that brings me to the end of this part of the talk. Overall, connecting back to what Noor said earlier, we are blessed to live in this phase of the 21st century, where we have so many new and exciting solar and heliospheric missions out there. We have Parker Solar Probe, we have Solar Orbiter. A week ago, the 4-meter DCAS telescope on Maui got officially inaugurated. It's like a microscope. It has huge resolution, but at the same time, of course, it images a tiny fraction of the sun, so we need to put that into perspective. And the movie in the background shows you a series of coronal mass ejections that hit Venus just a few days ago, and that was coincidentally exactly the time of Parker Solar Probe and Solar Orbiter being in the vicinity. In fact, we had our last Venus flyby on Solar Orbiter on the 4th of September. And literally, we were hit with the particles of a coronal mass ejection, and we got questions, are you okay? Is that something your spacecraft can take? And the answer was yes. In fact, this is what we asked for. We couldn't have asked for nicer solar activity in this phase of the mission. And that's really something that, with the rising solar cycle, makes the entire community really excited to work on this. And last week, with our first post-launch science workshop with over 200 scientists, especially young people that started their PhD during the dark days of COVID lockdowns. And it's really nice to see all of them coming together, work with this data. And so I think we have a couple of really good years ahead of us. And with this, I'd like to hand it back to Jason.
Okay, thank you, Daniel. Thank you, Noor. So Noor and Daniel have done a great job of staying on time, and that gives us 20 minutes for an engaging discussion with the audience, and we have many hundreds of people here. So before I wrap this up, I want to encourage everyone to send in questions. If you look to the right-hand side screen, you'll see the way that you do that. You go to www.slido.com, type in IAC 2022, and submit your questions, and I'll look at those questions on the iPad. You can also vote on questions that you see. If you think some of the questions are more appealing to you, go ahead and vote those questions up, and we'll start asking Noor and Daniel those questions. So to wrap this up, so first, thank you, Noor and Daniel, for a very exciting discussion of scientific discovery that's been enabled just in the last few years with these two incredible missions. We have literally only scratched the surface, right, with this exploration. Parker Solar Probe, the closest that Parker Solar Probe has come to the sun so far has been about 9 million kilometers. In the next couple of years, we're going to dive in even deeper to a distance of about 6 million kilometers. And if you look at Solar Orbiter, well, we're still pumping the orbit of this spacecraft above the plane so we can get that view of the poles, which we've never really observed before with this category, these kinds of instruments. So over the next couple of years, not only are the orbits and the science capabilities for these missions, because of their unique vantage points, going to increase, but the time of synergy between the two missions where they're working together with one another, there's going to be more and more overlap. And also with DKIST, as Daniel explained, our new ground-based solar telescope. Second, solar activity is increasing. The sun is becoming more interesting and more violent over the next couple of years. So this is really the perfect storm for understanding solar physics. Now I talked at the start when I showed you kind of this panorama of all stars in our galaxy and how the sun is responsible for life on all of the planets and all of the civilizations that exist in our galaxy and beyond. But it's also the case, as Noor was alluding to, that there are threats from the sun, right? You saw this video of solar radiation, energetic particles streaming from the sun. And fortunately, our planet Earth has a magnetic field, and that magnetic field protects us from a lot of that radiation. But we've seen events in the past where there's a massive coronal mass ejection that can overwhelm that magnetic field. It can knock out our power grids. It can knock out our telecommunication systems. And in a modern, technologically advanced society, it can also knock out our space assets, right? 10 years ago, there were 1,000 satellites orbiting Earth. 10 years from now, there's going to be 100,000 satellites orbiting Earth, both civil space assets as well as national security space assets. And so the study of space weather, understanding the nature of the phenomenon that generates space weather, and being able to forecast and predict these events so we can take care to help protect life and help protect our society and our infrastructure is going to be very important in the future, and both of these missions are contributing incredibly to that pursuit. Okay, so with that, we're going to wrap up the discussion of the lecture, and we'll move to the Q&A. Before I do that, everyone, please join me once more in thanking Daniel and Noor for a fascinating lecture. Okay, so again, if you have questions, go to slido.com, IAC 2022. There's a number here, so I will start, and I'll vector these to each of Daniel and Noor. Okay, so the first one is a good question. Okay, so what changes do you expect to see with the instruments that are on Parker Solar Probe and Solar Orbiter that we haven't seen before as the sun goes through the solar cycle, ramping up to solar max in 2025? So Daniel, do you want to start with that one?
Right. One of the things that we said Solar Orbiter would do as the cycle ramps up is study solar energetic particle events. So these are events that happen a couple of dozen of times per solar cycle, but they are the most energetic particle events in our solar system. We couldn't build a particle accelerator as powerful as the sun. So these events are in progress. I mean, there was one just 10 days ago, and they result in high levels of energetic particles that persist for several days until they gradually decrease. Essentially, the entire heliosphere, really literally in 4 pi space, is filled with energetic particles. And this is something that Solar Orbiter was set to build, and we'll get more of these now as solar activity ramps up.
Okay, thank you, Daniel. Nora, anything to add?
It's pretty similar for Parker Solar Probe. What Danielle said exactly applies to Parker Solar Probe, except that we are closer to the sun. For Parker Solar Probe, the environment, the harshness of the environment is key to the way we operate the spacecraft and the instruments. Most of the instruments, as I said, they are all in the shade of the TPS, but there are a couple of them. They are exposed to the full solar environment. And this, they have to survive whatever the sun is throwing at them. Also, in terms of operations, we have to adjust the thresholds of the instrument depending on the intensity of solar activity. But that's something we have to learn as we go. But overall, the spacecraft and the instruments are operating as they were designed, and everything is going well.
Okay, great, thank you. So the next question, so this is a good one that relates to space weather phenomenon. So what is the most reliable connection, right, in your minds between something that was observed and was proven between solar activities and phenomenon on Earth, ecological phenomenon on Earth or other infrastructure impacts, things of that nature? Daniel?
Yeah, that's a good question. It's probably harder to answer than to ask the question, but let me try anyway. So clearly, the most direct impact is in the near-Earth space environment. So there are examples, recent examples of satellites being taken down due to heightened solar activity. Essentially, the sun's activity increases the height of the ionosphere of our planet, and that reduces in increased drag for spacecraft. So spacecraft that are just being launched, like a few months ago, could then be brought down if you don't time that launch window well with solar events. So that is probably the most obvious one. Then there are spectacular ones that happen extremely rarely, like the power outage event in Quebec in '89, or the Carrington event in 1859. I think there's been a number of white papers published where they said if such an event like the Carrington flare happened now, it would have an economic impact of the order of several hundred billion euros or dollars. That happens, maybe it's a 1 in 100 years event, maybe even 1 in 1,000 years. But clearly, we are in a more, let's say, susceptible setting right now compared to 150 years ago. So we want to study what these extreme space weather events could be and what we can do to protect ourselves and astronauts in space.
Yeah, I would add probably now for commercial flights that are flying, that have polar routes, the radiation doses there, we have really to get a whole handle on. And the radiation doses, they do not necessarily require strong events. Mild events can still produce big radiation doses there. But let me say this. Our presence in space is bigger than ever. And what would be mild for us here on the ground may not be mild on the moon or on Mars or something like that. So we have to have a different view for space weather. It's a more global view than just us here on Earth. So if we want to send women and men back to the moon and hopefully soon to Mars, we have to know how to protect them. And to protect them not only from the extreme events, but also from the mild events as well.
Okay, so that's excellent. So there's a lot of good questions here, so let's try and go quickly and get to as many as we can. Okay, so Noor, this one's for you. So the question is about radiation hardening. How do we preserve the electronics of a mission like Parker Solar Probe? So maybe you could talk again about some of the temperature differences and the role that the thermal shield plays.
That's a great question. When we were designing Parker Solar Probe, obviously, mass is a critical parameter. There are certain limits that probably you cannot go. But also, you have to know how to protect your instrument in the spacecraft in the first place. We are going to places where the radiation doses are so big. They are the event that Danielle talked about earlier on September 5th, that the radiation, the particle doses we got from there are 100 times stronger than we measured a year ago. So these are really out of this world. They are big. So we have always to keep in mind that we have to protect the instruments, but also the spacecraft. So we have the right shielding material for it, but also we have to be careful that the spacecraft is not too heavy, that we can launch it and we can get it orbiting around the sun safely.
Okay, thank you, Noor. Anything you want to add to that, or? Okay, so I got one for you here. So let's see. So what do you expect to find at the sun's poles?
Well, clearly not Santa Claus, so he will probably not like it there. What we expect to find is the following. I mean, the current thinking of the sun's 11-year dynamo is a sort of conveyor belt mechanism that transports magnetic flux from the polar regions to the equator and then back to the poles in a subsurface layer. So this is a sort of convection role that we expect is going on continuously and would explain the solar cycle. But it's hard to constrain if you just look from the equatorial plane. I mean, you can, of course, create very sophisticated models, but a good model should be testable. And we are essentially lacking everything above 60 degrees latitude, because this is where the magnetic field measurements from the plane become unreliable. And that's what we believe to find, that we get high-quality magnetic field measurements that will enable us to either validate or reject current theories in terms of how the sun's activity cycle works. And using about 15 years worth of SOHO and SDO data, there was a study published in 2020 in Science by Guizon et al., where they showed that there is a flow with a speed of a bicycle, roughly 15, 20 kilometers per hour, that persists over years and could be such a convection role. But in order to really nail that answer down, we really need to get out of the ecliptic plane and take data from there and see if it fits.
Okay. Nor anything to add?
Well, just one small thing to add is, I think we expect surprises when we fly above the solar poles. I think many of you probably have seen the images of the polar region from Jupiter and Saturn, and you saw all these cyclones. We have been observing Jupiter and Saturn for decades and decades, but it's only when we flew above the poles that we saw them. We probably expect surprises like that on the sun. The sun is way, way bigger than Jupiter and Saturn in the first place.
That image from Juno was my wallpaper on my computer screen for weeks.
Yes.
So absolutely agree. Okay, so this one's going to challenge you guys a little bit. So you're in the thick of Solar Orbiter and Parker Solar Probe. You guys are spending a lot of time every day thinking about these missions. There's a couple of questions in here that are forward-looking. So put yourself in the shoes of somebody thinking of the next generation solar exploration beyond these missions based on what we're learning. What are you most excited about? In terms of science, in terms of technology, in terms of the kind of orbit that you have, et cetera. So maybe, Nora, I'll start with you, and then we'll hear from Daniel.
Well, if Parker Solar Probe and Solar Orbiter did something, it is the following. They are basically told us you can go after any ideas that we thought so challenging in the past, and we may not even see them happening. Now we are going after missions that are so challenging. If you think of it like Interstellar Probe, like the 4Pi solar mission, constellations that we not too long ago that we thought, yeah, these are probably too challenging, too expensive, whatever. But now we are thinking that the international community, we have to come together to realize these big ideas and these big missions to allow us to make big strides going forward in terms of exploration of the sun and its heliosphere. And all these big missions, it's basically for the future generations. It's for them, for the students, for the postdocs, for whoever, for even people who are not born yet. That's for them.
Yeah, I think I can only add to what Noor said. Clearly, one component where we've learned a lot is seeing the sun from more than one perspective. And the stereo missions, 2 spacecraft in orbit following and trailing Earth, have really been a great first step. But one could think about, let's say, a magnetograph on such a mission, where you can see essentially the sun's complete magnetic field, not just the front side, because that would really enable much higher quality inversions of the sound waves that travel inside the sun. Another thing that is conceivable is, of course, doing something that gives you a super high throughput, high quality image data and spectroscopy. That is something that can be easier done from near Earth orbit, but it would require bigger telescopes. So there are nice examples out there right now. But of course, I mean, we see new things at super high resolution with Solar Orbiter. I mean, that would whet the appetite of everyone saying, okay, but what if we go a factor 10 smaller? Would we see new things? Would we reach some sort of limit where you don't see any finer scale structures. We clearly see things we haven't seen with SDO, which is roughly a factor of 3. So one could want to push the envelope further and say, well, how about a factor of 10? Clearly, the sky's the limit.
Well, being a solar physicist, I have to be a little bit biased here. And throughout history, we have been observing the sun always from one viewpoint. And that is extremely limiting. It's not what we want to do. And remember, the sun is the only star in the whole universe that we observe from different vantage points. I think going forward, we have to aim for constellations that give us full coverage of the sun as a sphere. That's what we have to aim for.
Okay, that's great. And you guys actually knocked out a couple other questions that were in there as well, so thank you. Good job. Okay, so the next one is, maybe one of you can handle this one. So you talked a little bit about Parker Solar Probe and Solar Orbiter and kind of linking the data sets from both missions, but from different vantage points. Can you talk a little bit about whether and how you're able to do that with historical missions that are also observing the sun at the same time? So, for example, SOHO or Solar Dynamics Observatory, is that also a part of getting at the best science by combining those data sets?
It's not only about space, it's also about the ground-based observatories. And here I'm going to tell a brief story. When Parker Solar Probe get into encounter around the sun, there are certain orbits where we can see the whole encounter from Earth. And for those, we usually built a campaign for ground and space missions. The first one was encounter number 4, and we made an announcement there, hoping that a handful of observatories will support us. Guess what? We got over 50 observatories between ground and space supporting Parker Solar Probe. It's the same thing for Parker Solar Probe. Basically, these two missions are doing something that is unprecedented. They are bringing the whole international community to the same objective, which is understanding these big challenges, using all sorts of observations that we can have.
Yeah, I think that's exactly right. I mean, looking back at SOHO, we have a mission that's been operational since early 1996 and is still going strong. And there's a commitment to keep SOHO running until a coronagraph on the Sun-Earth line is operational, which might be the case in just a few years' time. But we have this huge archive of data spanning 2 solar cycles, and that we can, of course, harness to learn more about the new events that we see. And the LASCO coronagraphs are still taking data, and so we can complement that with what we have. And I think what Noor said was exactly right, that there's so much added value in getting people to collaborate because everyone can bring extra data to the table. There's the Bepi-Colombo mission en route to Mercury, still in cruise phase, but they have some instrumentation already working and already on. So when there's a CME, a coronal mass ejection, we can simply ask them, what data do you have, and get another additional data point to better understand what happens physically. Because that's the one thing you can't do as an astronomer. You can't run the experiment. The experiment is running for you all the time, and the best you can do is have your probes in as many locations as possible.
Yep. Okay, great, thank you. So I'm going to try and squeeze in 2 more. So this one's going to go to both of you, but very quick answer, please. What is the life expectancy of each of the missions?
Right, for Solar Orbiter, it's 10.3 years. That's the guaranteed lifetime that we got from our prime contractor, based on fuel and solar array degradation. We got the picture-perfect launch. We saved a lot of fuel right there. So in terms of fuel, we could probably keep going much longer. In terms of solar array degradation, it depends a bit on solar activity, but usually there are some healthy margins in what you get from good engineering.
For Parker Solar Probe, the prime mission is 7 years long, and we already 4 years into the prime mission. By the end of the spacecraft, by the way, is healthy as we launched it, and it's really doing well. So what we expect by the end of the prime mission is the mission will be extended. In terms of fuel, the mission can go for over 50 years. What will be limiting are other subsystems. That probably, as Danielle said, the effect of solar activity and solar radiation will probably be limiting. But in terms of fuel, there is no shortage there. We are fine.
Okay, and the final question is going to be, what has surprised you the most about each mission? So Danielle, why don't you go first?
That's a difficult one. I think in a nutshell, I was surprised how many of the big ticket items we could check off within half a year after going into our nominal mission. It's usually, I mean, if you ask a scientist to get the sort of woolly answer and say, yes, we'll do that, probably takes a couple of years and we need some more funding as well. But we actually checked off some big ticket items within the first half year, and I think that's most remarkable for me.
The surprise for me are probably two. Back in 1 year before launch in 2017, we had a workshop at EPL trying to make predictions what Parker-Solar probe is going to see. Trust me, all the predictions were wrong. None of them were right. The other thing also, when we were building up to the launch, there were some meetings in the science community saying, okay, what are the low-hanging fruits? Guess what? None of them. Because everything, basically, what we saw is kind of new. And that was the big surprise to all of us.
Okay, so with that, we're going to close up the session here. I want to thank both Daniel and Noor for bringing these two international missions together at IAC. This is a perfect venue. Thank you to the organizers for selecting the highlight lecture, and thank you to all of you for coming, and please enjoy the rest of the International Astronautical Congress. Thank you.
Thank you.